Okay, thank you for attending. So today I'm going to share our paper for second 2024. The name of the paper is on the sensitivity of individual fairness measures and robust algorithms. So probably first, a brief introduction of myself. My name is Xinyu, and I'm a third-year PhD student from University of Illinois at Urbana-Champaign. And my research mainly focuses on graph learning, including like graph generation, graph trustworthy learning, and also graph-based recommendation tasks. So here's the outline for today's presentation. First of all, I'm going to introduce the background for individual fairness and some related stuff, and discuss our motivation, proposed methods, and present our experimental results. And finally, I'll draw to the conclusion. So first of all, let me introduce the background for individual fairness. So you may be familiar with many kinds of other fairness, like group fairness, which is actually the most popular one. But individual fairness consider the fairness on the finer granularity. So it is rooted in the dictionary definition of fairness, which is I cited below from the Merriam-Webster, that is defined as lack of favorism toward one side or another. So in the definition of individual fairness, it tries to treat like cases alike. A most popular way to implement individual fairness is through Lipschitz property, that we want to get similar outputs from similar inputs. A visualization is from the below. So technically from two inputs, which is X and Y, which is represented by two people here. When we are going through a fair machine learning model F, the distance between the outputs, which is Fx and Fy here, should be bounded by a bound. So individual fairness has its advantage compared to other fairness because it is considering fairness on a finer granularity. Consider that in a group fairness where there's many minority groups and some of the groups you might not be able to identify. So this is when individual fairness become more effective because you don't have to define the groups in individual fairness. So you can protect whatever groups you want. So our paper is based on a evaluation and rethinking of a previous work on individual fairness, which is a KDD 2020 paper. It is called Inform Individual Fairness on Graph Planning. In this paper, it defines the input distance matrix as the Euclidean distance, the output distance matrix as the square Euclidean distance, and the input distance matrix as a predefined similarity matrix instead of a distance matrix. So you can consider the similarity matrix as the inverse of a distance matrix. So based on the Lipschitz property, the definition of the individual fairness will become the first line. The left-hand side is the square Euclidean distance. The right-hand side is the inverse of the similarity over error bound epsilon. And so this is a strict bound for each entry in the similarity matrix. So the author loosens the bound and gives a definition of individual fairness bias by summarizing all error bounds from all the ij's in the similarity matrix. So it gives, when we are summarizing the epsilon from all the inequality in the first line, we're going to get a trace-like individual bias. And this is the definition we'll adapt in this paper as well. Based on this individual bias proposed in this paper, the author also introduced several techniques to implement the individually fair machine learning algorithm. One of the algorithm that is easy to implement and easy to work is based on adding a regularization parameter that we directly introduce the individual bias in the loster. So we'll get L tilde is equal to the original loss function of the learning model plus the individual bias timed by the regularization parameter. So this line, unlike in other works, typically other machine learning works, it considered the y, which is the output, as the parameters to maximize, to minimize, to optimize. But it's the same way as we do for other machine learning models when we optimize the theta. It's only that we consider it in another way. However, a problem in individual fairness and also in this paper Inform is that the similarity matrix is hard to define. So you can imagine that in the inputs, there are going to be multiple kinds of dimensionalities, multiple types of data. And so it's hard to define the distance between the inputs. But for the outputs, the D1, normally it's the vector or some statistics. So we can use some like Euclidean distance, cosine similarity, or like chaos divergence to define the distance matrix. So in this paper, we're going to take one step forward to solve the problem of defining the input similarity matrix. So here's the motivation for our work. So first of all, given different input similarity measures, ensure that the output is going to be largely different. And there is, as this is a long-lasting problem in the fields of individual fairness, so there actually is a lot of work that has been focusing on this problem. So one way to do from previous work is to add some learnable individual weight parameters for different features in the similarity measure. So, however, learning a weighted similarity measure from a complex objective function can be really unreliable because it is hard to tell whether the similarity measure we learn promotes individual fairness or instead penalizing individual fairness in trade of better model utility in general. And another group of works try to include human feedback or annotation or judgments, which requires a lot of human effort, which could be expensive. And their measurements would be task specific, and also the human judgments themselves could also be biased or malicious. So right now, there's no perfect solution for this problem. Therefore, we point out in this paper that it is important to understand how system-based biased learning outputs with respect to the input similarity measure changes. So in this paper, we defined the problem 1, which we refer to as the SOM problem in the right upper side corner. Is to measuring this problem is to measure the sensitivity of individual fairness that given a data set and the predefined similarity matrix, and also the individually fair learning outcomes from the Inform paper. We try to understand under perturbation how the individually fair learning outcomes will change, which is the delta Y star here. And we only consider the case where the perturbation, where the similarity is symmetric. So the perturbation is symmetric as well, because in this case, the similarity between I and J is the same as the similarity between J and I, and which is a common scenario. So as long as we have the evaluation of the sensitivity of the individual fairness, we want to take one step forward to ensure that the individually fair learning algorithm is robust to the change in this similarity matrix. And we also want to point out that the input similarity is an additional source for attacking from malicious users. We did some experiment to attack the Inform algorithm by adding some L infinity constraint noises to the similarity matrix, and part of experimental result is shown below. We can see that the performance dropped a lot after we add a noise, and also using some other attack technology like the PGD, which is the projected gradient descent, that takes small gradient-based steps and projects the perturbed example back into the allowed epsilon ball around the original input, and also the FGSM attack, which is the fast gradient sign method that is a one-step attack that adds a perturbation in the direction of the sign of the gradient and scaled by epsilon. So based on this observation, we proposed the second problem, which is to design a robust individual field learning algorithm. And we refer this problem as the SOA problem. So in this problem, given a data set D, a similarity matrix S, and same inform algorithm, we want to get a revised similarity matrix, which will be lead to a less sensitivity for the algorithm, and also the revised individually fair learning outcomes that comes from the robustified individual fairness algorithm. And for the when we say the revised robust individually fair outcomes, we hope that it is first as close as possible to the original optimized outcomes, learning outcomes, so that it could preserve its utility. And also it will be robust to the perturbation on the simulation measures. So next, you go to the proposed methods. First of all, we will focus on the SOM part, which we want to measure and quantify the change of individually fair learning outcomes in response to a symmetric perturbation on the input similarities. So obviously, there's a naive solution to the problem that we can do by retraining. However, we want to point out that this is very computationally expensive, which is not tractable. So we resort to local sensitivity analysis, which uses the partial gradient and estimate the model's response to infinitely small change in S by using the first order of the Taylor expansion. So after the first order Taylor expansion, if the changing model's outputs is gonna be the summation over gradients times the change in S, which is the delta S here. However, to calculate this changing model's response, we need to calculate the gradient of Y star with respect to each entries in similarity matrix first. And this gradient estimation is non-trivial. So we have to use some other tactics to speed up the process. And influence function is a powerful tool for understanding model behavior that has also been widely used in other fields like data attribution or data evaluation. So we'll use this tool to estimate this gradient in this paper. And this influence function is based on the assumption that the loss function for getting y is twice differentiable and strictly convex. This is a bit tight constraint. But in the original paper of the influence function, they also point out that even though it doesn't satisfy the assumption, the calculated gradient is still gonna imply some of the information. And also we did some experiments on convex but not strictly convex function, and I will show later in the experiments part that our method is still working. So let's start with the mathematical derivations for deriving the change in the model outputs. Here's the outline for the whole derivation process. So first of all, we are gonna use the influence function to calculate the gradient of the outputs with respect to the similarities. Then we will plug it into the first order approximation equation. And finally, we are gonna get a formula as shown on the right side. So before we start deriving the gradients, we applied a vectorization trick to vectorize the output of y. So in a machine learning algorithm, the output is gonna be in the shape of n times d. But if we are using the n times d shape of the y star, when we are deriving the second order gradient in the influence function, the second order gradient is gonna be a four-dimensional tensor of a shape n times d times n times d, which is not easy to understand and easy to derive. So we first vectorize the output of y star and do the calculation based on that. So in the first step, we're going to apply the influence function on the right upper corner here, which is the original function of the influence function. Basically, it says that the change in the output is gonna be minus 1 over n times the inverse of the Hessian matrix and times the 2 times gradient of the loss function with respect to input x and parameter theta. So if we are estimating the gradient, we move the delta from the left-hand side and we will get the first line here. That the minus 1 over n, and n is a number of non-zero entries in the similarity matrix, the inverse of the Hessian matrix, and the gradient of the loss function of inform. So the upper so the L plus alpha trail here is the loss function from inform with respect to the input x, which is s here. And also the theta that we consider in our case is the vectorized y here. So this is a formula of applying influence function into our case. And the Hessian matrix is going to be the second order gradient of the loss function as well with respect to the vectorized parameters, which is the vectorized y here. We can further simplify the Hessian matrix into the following form, which would be more simpler. And we can observe that in the first line, when we are applying the influence function, the first term loss function is gradient with respect to s is actually 0 because we assume that in the original learning model, it is not using the similarity matrix between the instances. So we can remove this first term and only keep the second trill-like term and derive the gradient as following term, as the following form. Okay, and this is for the first part, and continually on the calculation of the influence function, we get a following form from the previous slides, and the Laplacian here, if you may be familiar, the Laplacian is the degree matrix minus the original matrix. So the gradient of the Laplacian with respect to the original matrix can be directly derived, and we can rewrite the whole thing into seemingly more complex stuff. But actually, when we are rewriting the inverse of the Hessian matrix and put alpha inside, we can get a more cleaner formula below. So
Sorry,
this is
I have a
gonna be
question.
Mhm.
So you said that you can basically reflect the Laplacian with respect to the initial similarity matrix,
Yeah.
because it's based on the adjacency, right? But
Yes.
what if for the similarity matrix you're not using the adjacency? What if you're using, for example, the cosine similarity of the input features or
Uh,
a different similarity function, right? I think in the Inform paper they had many different similarity functions.
yeah, so the Laplacian here is the Laplacian of the similarity matrix. So
Okay,
not the
sorry. Yes, I
adjacent one.
understand.
Yeah, yeah.
Gotcha.
Yeah, because in the loss function is the Laplacian matrix, the Kronecker product of the Laplacian and the identity matrix.
Totally. Silly mistake.
Okay.
I got you.
Okay, and no problem. And so from this step, we'll have the gradient of the vectorized y star with respect to every entry in the similarity matrix. So in the next step, we want to do the first order as estimation to summarize over all the entries to get a final changing outputs for the delta y star. So here's the derivation part that first of all, we start with plugging in the first order estimation by plugging in the theorem one that we just got. And so this one is based on, this one has a summation over 3 terms, which is n times d, and so we did some reparameterization, some rewriting, and we make it into nd times nd, which will fit the output size of the vectorized delta y star. So there's actually a little trick from the division from the second line to the third line. You can see that from n times n times d to nd times nd, there's a gap between them, but I wanted to clear that this equation holds because we are considering the delta S, the connected product of delta S times an I identity matrix. For this is a block diagonal matrix. So when I minus j is larger than capital N, this one is gonna be 0. So the equation holds. And finally, by rearranging the third line, we'll get the final estimation of the change in the output y star, which is quite clean here, which is, and I rewrote it into minus 2 alpha w, and w is the, if I could remind you, so w here is actually the n times uh, the n times h n times inversion of the Hessian matrix. So n times connected product and also a vectorized y star from the informed paper. Looking at the formula, we can observe that it is having a form like a matrix vector product. So W here is a big Hessian matrix that involves the inverse of the second order gradient. And the part that includes Laplacian connected product, identity matrix, and vector y star, this part is going to generate a vector of size n times c. So it's basically an inverse of a matrix times a vector. So if we're trying to directly derive the matrix W, or which we'll refer as the SOM matrix, it's gonna take the time complexity of n cubic times d cubic, which is not acceptable. So we apply a similar strategy like in Hessian vector product to speed up the process. The Hessian vector product is to calculate the multiplication between a model inverse with a vector. So the so the methodology in Hessian vector product is that when we calculate the Taylor expansion of the inverse of the matrix can be expressed as on the upper side here. Which is a summation over j equals 0 to infinity, I minus the identity matrix minus the matrix to the j's order. And when the maximal altitude of the eigenvalue of the matrix B of the matrix I minus B is bounded by 1, then this series which is represented by I minus B to the J will converge to 0. So we can use an iterative way to calculate the Hessian vector product. And by writing it in the form of a code, it can be formulated in the right-hand side here. Basically, in each round, we will update it with the vector plus identity minus the matrix times the result we get from the last round. And by applying this Hessian vector product, we can reduce the time complexity to k times m times d, where k is the number of rounds we do the Hessian vector product, m is the number of entries in the similarity matrix, and d is the output size of the y star. And also note that as we're doing a slight change to the Hessian vector, because our W is n times the Hessian vector, so we need to add a scaling factor to guarantee the convergence of the whole Hessian vector product process. And we provide proof in our paper that the scaling factor C exists by using the circle theorem. And in practice, we utilize the scaling factor equals to the reverse of the first order norm of the inverse of the SOM matrix. I didn't put a proof here, but more data can be found in our paper. So in this page, so I'm going to instantiate the SOM matrix with 3 popular machine learning algorithms, including the ranking, clustering, and classification. And more detailedly, it will be the PageRank, spatial clustering, binary cross, and triple loss. The formulas are summarized in the matrix below. The rightmost columns is the SOM matrix derived from our algorithm, which is generally all quite simple to derive and also in a neat form. And I also want to note that the spectral clustering is a convex but not strictly convex algorithm, which is in conflict with the assumption in the influence function that it has to be strictly convex. But I will show later in experiments that the estimation is still valid. So for now, we have the formula to estimate the change in learning outcome with respect to a perturbation delta S. So taking one step forward, we want to design a individually fit algorithm that is robust to the change in the input similarities. So we consider the perturbation under the L infinity constraint. So our goal is going to be minimizing the largest change of learning outcome under the perturbation within the L infinity constraint. So based on our previous theorem, we first defined approximate distortion, which is going to be the sensitivity of the whole algorithm, which is a delta y star here. And it is the response of the model with respect to the input distortion delta S. And we use the Frobenius norm to estimate how large the distortion is. And based on this approximate distortion, we formulate the whole problem as a nested bi-level optimization problem, which is gonna have 3 levels here. So the highest level, which is the minimization here, is gonna to optimize the similarity as tilde to minimize the sensitivity under the worst perturbations. And the second level, which is the middle level here, we want to find the perturbation delta S that will lead to the worst sensitivity and leads to the largest approximate distortion. And in the lowest level, in the approximate distortion, as we are using the Y star here, we also need to solve the optimization of the informal algorithm to find the best individually fit learning outcome with respect to the given similarity measure. And we enforce that the perturbation delta S is in the L infinity constraint. And also we want that the change of the change of the similarity matrix, which is the S tilde minus S here, is also constrained. So although this is a nested bi-level problem, we want to point out that there's no connection between the inner level, which is the optimization of the Y star, and also the optimization of Y star, and also the optimization of the Laplacian of the of delta S, and also the Laplacian of the similarity matrix. So we can train it within alternative training paradigm. And so in each round, we're going to update the Laplacian of the similarity matrix first, as updating the Laplacian is having the same effect as updating the original similarity matrix. And in the second round, in the second step, we are going to update the output of the informal algorithm, which is the Y star here, and also finding the worst perturbation that will lead to the largest approximate distortion, which is the delta S here. And to enforce the infinity constraint on the input delta S, we use a reparameterization trick that we re-rotate into epsilon times tangent h cube, where q is not bounded by 1, but so that delta, but the tangent, but output of tangent h is gonna bounded by 1. So delta S is bounded by minus epsilon to epsilon. And also consider that we are assuming that the algorithm is strictly convex. So ideally, when we are reaching the maximized distortion, the Q should be close to infinity or minus infinity. And for the second constraint that we that is pushing the the updated similarity matrix to the original similarity matrix, we did not explicitly control it, but instead we control the change in the similarity measure by controlling the update limit by updating limited iteration, so it won't change too much. So this is the overall algorithm for the SOA part. And we are going, so this is all for the methodology, and I'm going to move forward to the experiments to show the effectiveness of SOA and SOM. For the experimental setting, I'm using the algorithm that we just instantiated, which includes the PageRank, spectral clustering, and binary classification with the binary cross entropy loss. For the input similarity measures that we are testing its sensitivity, we apply two measures, including the cosine similarity, and also the Jaccard similarity. So cosine similarity is a number based, like that you consider the cosine similarity, and Jaccard is more of a graph structure based that counts how many similar neighbors you have. And by the matrix, we have several matrices here. So first of all, we want to estimate how close is our estimation of the changing outputs given by SOM compared to the actual change by rerunning the experiments. So the delta Y star here is gonna be the estimated changing outcome given by SOM. And for the Y star from in below, we rerun the whole algorithm by adding delta S to the original similarity matrix and get the difference between the one after adding perturbation and the original one as the ground truth. So this two matrix scale error and error rate is estimating how accurate is our estimation delta Y star with respect to the ground truth given by rerunning the whole algorithm again. And by evaluating the effectiveness of SOA, we are going to introduce three aspects of evaluation matrix, which include the sensitivity that measure the L infinity norm, the infinity norm of the change in the output. And also the utility side, we have the NDCG for PageRank and accuracy for binary classification. And we adopt the individual bias introduced in Inform as the measurements for individual fairness. And we test our algorithm on 5 graph-based data sets and 3 non-graph data sets, which statistics are summarized in the right-hand side. So here's the experimental result. So
Sorry,
first
can
of
I
all,
ask I have another silly question. If you go back one slide, I don't know if I understand how you apply the PageRank algorithm to a non-graph data set.
oh yeah, sorry, I didn't introduce. So we are only testing PageRank and spectral clustering on a graph data set and the binary classification on the non-graph data sets.
Gotcha. Sorry, thank you.
So for the SOM problem, we want to estimate how accurate is our estimated change in model compared to rerunning the whole algorithm. So as you can see, our scale error and error rate is all below 1 in most cases, except for this one. And they are generally close to 0. So which means that our estimation is close to the result via retraining, and they are on the same scale. And an interesting observation is that the Jaeger similarity is actually more stable than the cosine similarity for PageRank that you can see. This one is Jaeger similarity is the change in the output is generally smaller than the one for cosine similarity. And on the contrary, for the spectral clustering, the sensitivity of the Jaeger similarity is going to be larger than the cosine similarity. And this result, I think, is consistent with the intuition because the PageRank depends solely on the graph structures, so it would be more suitable to use the Jaeger similarity, while the spectral clustering often applies cosine similarity to further do the clustering. Therefore, the cosine similarity would be more suitable for it. And for the experimental results for the robustify algorithm, so we put part of the experiment. I put part of the experimental results here, and we can see that the sensitivity largely decreased compared to Inform, and also the we effectively increased the model's performance under perturbation that for the two rows with perturbation. So the WP here is abbreviated for with perturbation. So we reach a higher performance compared to Inform on the other circumstances that perturbation is added. And also in the cases of original field learning algorithm, we also improves the performance of the model in most cases. However, we are having a slightly larger individual bias compared to Inform. This is because there's a trade-off between the fairness and also for the sensitivity and utility. But we are only increasing not that much. Actually, only a little bit of increase, so this is acceptable. And from another side product from the solver algorithm is the delta S that we optimize to maximize the sensitivity. And we use this delta S that we consider it to maximize the sensitivity of the individually field learning algorithm to attack the informed algorithm. So part of the experimental results are shown below. That our attacking method is not achieving the best attack performance in all cases, but we have a good performance on several terms, like under the Jaeger similarity for the two data sets. So this one proves that the similarity measures can indeed be an effective source of attacking learning models utility, which emphasizes the importance of learning a robust individually fair algorithm. And another interesting thing I want to note is that PGD and FEGSM is, which are two baselines here, is leading to a higher individual bias, while our attacking method does not. So this is all for the presentation, and I'm going to summarize the content of the paper here. So for the problem, we introduced the sensitivity analysis problem of individual fairness. And for the SOM problem, we try to measure the sensitivity of the debiased learning outputs with respect to the input similarities. And by designing the SOE algorithm, we propose a robust individually fair learning algorithm via nested bi-level optimization. And in our extensive experiments, we show that two methods, SOM and SOA, are effective for measuring and reducing sensitivity. So generally, this work contributes to a broader problem that how robust is existing individually fair algorithms with respect to the similarities, like how existing works, if the existing works is stable with the inaccurate similarities. And furthermore, we hope that our works can utilize some other works to find a more reliable similarity measure by robustifying the individual fairness algorithm. So that's all for the presentation. Thank you for listening. And if there's any questions.